All right, so these are the physical state notes. So if you were gone from class, then this is how you're going to get those. You can pause as often as you need to get these, but I already have them typed out because then I don't have that pressure of typing while somebody's watching me, right? So even though it's just a camera. Okay, so physical states. We're about to enter, or we are entering our third unit, and this is air chemistry. And so we're going to talk about the three physical states, and then we're going to really focus on gases moving forward. So the three most common physical states on our planet are solid, liquid, and gas. Solid, liquid, and gas. And the difference between these three physical states, the differences between these three physical states have to do with distance between the particles and motion of the particles. So we've talked about these before. We did a little introductory activity with these early in the semester, but now we're going to get into a little bit more detail. So we're going to break these each down: solids, liquids, and then gases. So for solids, the particles are closely packed together, so they're very close to each other. They're, in fact, touching would be even more ideal for this picture. It didn't quite get them touching there. They're arranged in an orderly pattern. So easiest way to show that would be rows and columns. That's not how all atoms in a solid are arranged. It depends on the solid, but rows and columns is a really easy way to show that they're orderly. And so that's showing you understand that they're orderly. They're in constant motion. So they're vibrating in place, and that's not, they're not flowing past each other, but that is constant motion. All of these particles are vibrating in place. They're not moving around each other, but vibrating. And they're strongly attracted to each other. And that's what holds them close to each other. Sometimes that strong attraction gets to the level where we would call it a bond, and sometimes it's just a strong attraction without fully being a bond. But either way, it's a strong attachment there. Common solids, metals, all the metals except for mercury are solid at room temperature. Most ionic compounds, metalloids, and if you remember from our color-coded periodic table, the ones that are on the stair-step line are the metalloids. And covalent compounds with large molecules. So sugar is one example. This is table sugar, C12H22O11. That's really one molecule with that many atoms in it. That's really large. So large molecules are going to end up being solids. And so then draw yourself a quick particle diagram of the solid. Now this solid diagram is only showing one kind of particle, so this would be maybe a pure element, okay? If we had a compound that had two different kinds of atoms, then maybe we would have used alternating colors to show that it was made of two different atoms, or we could have done like one open circle, one filled in circle, things like that. So just be aware that orderly arrangement and close together and vibration indicators here, that's a solid, whether it's made of one kind of particle or multiple kinds of particles. All right, next, liquids. The particles of a liquid are in contact with each other, but not tightly packed. So here we're still touching each other in some places. A couple are spaced out, but they're still in contact. They're constantly moving, flowing past each other, and colliding with each other. So they're rolling around, moving past each other. And they're attracted to each other, but not very strongly. So they're attracted to each other enough to stay near each other, but not enough to hold each other rigidly in place. Okay. So these little tails that are in here, the little whooshy lines, those would indicate flow, instead of the ones up here for the solid would be vibration. Okay, so flowing through and around each other is what I was trying to go for with that picture. Common liquids, well, there's only two elements on the entire periodic table that are liquids, and that would be mercury and bromine. And if you're looking at the periodic table that I've given you, the Plainsman periodic table, that maroon and white one, those are the two elements that have a blue symbol. So mercury is Hg and bromine is Br, and those symbols are colored blue on our periodic table because those two are liquids at room temperature. Covalent compounds with smaller molecules like water are also going to be liquids. All right, gases. The particles of a gas are not in contact with each other, except when they bump into each other. So these are flying around. Oh, I forgot the whooshy lines on that one. But they're flying around, and sometimes they're going to bump into each other and collide, and that's going to end up being some contact, okay? But they're not constantly in contact with each other. They're just flying around freely. And speaking of that, they're flying around in straight lines. They don't take a curve in the middle of nothing. They have to hit something to change directions. And they're not attracted to each other, which is why it's a gas. Those particles are spread apart, far apart from each other, because there's no attraction to hold them closer to each other. Common gases are going to be some of the nonmetals, not all of them. So nonmetals is not the same thing as gases, right? Like carbon is a nonmetal, but it's a solid. But some nonmetals are, and those ones have red symbols on our Plainsman periodic table. So our gases have red symbols: oxygen, nitrogen, hydrogen, all the noble gases, okay? So just look for those red symbols. And then some small covalent compounds are also going to be gases. So for example, carbon dioxide, that's a compound that we breathe out. And that one it's very small. It's got 3 atoms, and it is a gas. Now water's got 3 atoms and it's a liquid. Carbon dioxide has 3 atoms and that's a gas. If you are to take a further chemistry course, Chem 1 maybe, or a college chemistry course in the future, you'll learn about things called intermolecular forces of attraction, and it'll help explain why some of those are gases and some of them are liquids. Okay, we're going to talk about the energy of the 3 physical states and then the volume of those 3 physical states, and then that will be the end of these notes. So the energy of the 3 physical states. Well, first of all, this is huge right here. Energy depends on temperature. Temperature is key. So hopefully you already have that sort of in your head. If you heat things up, they become more energetic. Okay, you are putting energy into them, they are becoming more energetic. Okay, so if substances are the same temperature, then they have the same kinetic energy, the same energy. Okay, so if you're looking at air inside my water bottle, okay, this example here, the particles of the air inside my water bottle, that's a gas. But then I also have water inside my water bottle, that's a liquid. And then the water bottle itself is a solid. I've got solid, liquid, and gas all together in my water bottle, okay? They all have equal energy because that entire bottle of water is all one temperature. Okay, so their particles have an average amount of energy that's the same across the board. They're moving in different ways. The gases are flying around, the liquids flowing around, the solids are vibrating in place, but the amount of movement is the same overall. Okay, so that lots of vibrating in place, when you add all those little jiggles up together, that's the same amount of movement as a gas particle flying through. So their average energy is the same. They're the same temperature. But for a given substance, if you just pick one substance, okay, just a single type of substance. So up here in my water bottle, I had a bottle, I had water, and I had air. That's 3 different things, okay? But for a given substance, one substance, the 3 physical states do not have the same energy. And so we'll use water as an example since we're really familiar with water, okay? So water, solid water, which we call ice, has the lowest energy, okay? Because it's cold. Cold is low energy, okay? Liquid water has more energy. And there's a lot of temperatures of liquid water, right? Like just barely liquid, really, really cold water, it has less energy than almost boiling liquid, which is really hot water, right? So you can get more and more energy within a liquid. Then you get to gas water, which we call steam or vapor, and that has the most energy, and that's because it's hot, okay? So we go cold to hot, you get more energy. So just keep that in mind. It's not about solid, liquid, gas, it's about temperature. So if I have a solid, a liquid, and gas at the same temperature, same energy. But if I have a solid, liquid, and gas and it's cold to hot, then I'm getting more energy. Okay, volume of the three physical states. First of all, solids and liquids, okay? I'm going to scroll back up to their picture here in a second, but solids and liquids have their particles touching. So if I change from one to the other, like melting or freezing, it doesn't change the volume very much. So I'm going to scroll up and show you what I mean by that, okay? The particles should be touching if this were a really perfect particle diagram, and here they're touching. Practically most of them are touching, okay? If I take this and I freeze it and turn it into a solid, really what's going to happen is they're just going to stop flowing and they're going to line up in a nice orderly pattern, but the volume overall doesn't change. They don't get much closer to each other because they're already touching, okay? Likewise, if I melt this, they're going to start rolling around each other, but they're not going to be spreading further apart, okay? They're still in contact. So volume change between solid and liquid is not very much. It depends on the substance how much it is, but it's not very much, okay? In contrast, gases have a lot of empty space between the particles, a lot of empty space. Before I continue with that, I'm going to scroll up to the picture here. In between these particles is empty space. So if you want to draw an arrow to this space here and label it literally empty space. There is not air between the particles of a gas. Air is a gas, and between the particles of air, there's nothing. There's nothing there. It's empty. The volume of air is mostly empty space, which is why it's so easy for us to walk through air. It's not as easy to walk through water because there is not empty space there. You have to push those particles around you, make them flow around you instead of just make them bounce off of you and fly through the empty space, okay? So down to here again. Gases have a lot of empty space between particles. So boiling a liquid, which is turning it into a gas, makes this substance take up a lot more volume. So if I take a liquid and I boil it, the particles go from touching to being really spread out with lots of empty space. So we are massively increasing that volume. Condensing a gas, which is turning it into a liquid, causes a dramatic shrinking of volume because all of the empty space goes away. I take a gas where my particles are super far apart and I turn it into a liquid, boom, now they're all touching, all that empty space just disappeared. So the volume massively shrinks. And you're going to see an illustration of that in the can implosion demo video. If you haven't seen that yet, you're going to see that, okay? So that is the notes. I'm going to put a link for the can implosion video in this same announcement so that you can watch that and you can do that activity as well. So thank you for watching and we will see you in class.